This class is about machine learning. So what exactly is machine learning? Let's begin with programming first. Programming is kind of automation tool. Suppose you have a problem to solve and you know how to solve it. Then you write the program to solve the problem, right? So once the program is done, and the rest is easy and automatic. Okay, you simply run the program and the program solves the problem. You don't have to worry about, right? So that's programming. So we are good, we are happy. Then why do we need machine learning? The problem is, suppose you have a problem to solve, and the problem is sometimes you don't know how to solve the problem, or even though you know how to solve the problem, the program is very complex, right? So in that case, virtually the programming is almost impossible. So in that case, the tool we can use is machine learning. Okay, so instead of writing program by yourself, you can use machine learning technique to write program automatically. So in that sense, machine learning is sometimes called automatic programming, or in this slide, it is called automating automation. So instead of you writing programming, you get the computers to program themselves. Okay, so as I said, when you can use machine learning when writing software is the bottleneck or impossible, right? So instead of writing program, you let the data do the work instead. So that's the beauty of machine learning. Difference between traditional programming and machine learning approach. So in traditional programming, so you want to solve a problem, then you write a program like this, whether you can use C, Python, Java, you name it, whatever, okay? Then once programming is done, the program reads input data and generate the output. So it is your job to write the program here. On the other hand, in machine learning, to solve problem, actually what you do is to given input, you provide its corresponding output. So given this input data, the output should be like this, something like that. Okay, so you have another input data and its corresponding output should be like that. Okay, so you have a lot of these pair of data and feed them to the machine learning algorithm. Okay, and then this machine learning algorithm generates program as an output. So in machine learning approach, program is output. Okay, here the programming is input. So that's difference. In traditional programming, you write program, and in machine learning approach, you provide data and the algorithm generate program. So that's why this is called automatic programming. Okay, so that's the main difference. So in machine learning approach, you don't have to worry about programming, and this is very easy, automatic, simple, efficient. Okay. So that's the advantage of machine learning. Uh, Before I move on, I'm going to emphasize one thing here. So when I say program in the context of machine learning here, this program is not actually the traditional programming language like C, Python. This program here means machine learning models. Okay, so this is not the program language program. Okay, it's just machine learning model. Usually this program means just a bunch of numbers, matrix, arrays. Okay, so that's different. This is not the like C program, Python program. This means machine learning models. So the machine learning generate program out of data, and sometimes it sounds too good to be true. Almost it sounds like magic. So, but actually, machine learning is can be kind of compared to gardening in your home. So in gardening, you plant your seeds by scattering them, and you provide nutrients or fertilizer. Okay, then later on, if you have enough water and sunlight, the seeds grow into plants, right? So it's similar in machine learning. So in machine learning, you have your algorithm, and then you provide data to the algorithms, and then algorithm actually gonna generate program as an output. So in this case, program means machine learning model. So in that sense, machine learning is quite similar to the gardening job. Okay. This slide shows the definition of machine learning from Jeffrey Hinton, who is known as the father of deep learning. So, as I told you, sometimes it is very difficult to write program to solve problems, like recognizing faces. So, so in the case of recognizing faces, we don't know how to program it, okay? And even though we have a very nice idea of how to recognize faces, the program is extremely complicated. So in this case, instead of writing a program, which is very difficult to do, that we collect a lot of examples that specify the correct output for a given input. So you collect a lot of examples with input output, okay, with input and its corresponding output, and then a machine learning algorithm actually takes these examples, and somehow the machine learning algorithms figure out how to solve the problem. Okay, and then the machine learning algorithm produces a program. In this case, machine learning model produces program that does the job. Okay, so by providing a lot of input-output sample to the machine learning program, in this case to solve the recognizing face problem, then machine learning algorithm somehow figure out the algorithm, the method, the logic there to recognize face, and then produce a program machine learning model to solve the problem. That's the beauty of machine learning. So the program produced by, I told you, program produced by learning algorithm may look very different from a typical handwritten program. As I said, the output generated from machine learning is not actual program, it is machine learning model. Actually, it contains a bunch of numbers, sometimes millions of numbers. Okay, so if the machine learning algorithm is correctly trained, the program, I mean the machine learning output, works for new cases as well as the ones we trained it on. So that's the advantage of machine learning. This slide is a little redundant of a previous slide. And when do we use machine learning? So actually, we use machine learning when the first human expertise does not exist. So sometimes we don't know how to solve problem. Okay. So in that case, we use machine learning. The second case is humans cannot explain their expertise. Humans know how to solve problem, but he cannot express or explain what he knows, right? In that case, we cannot write a program, so we have to use machine learning in this case too. And the third case is the models are based on huge amount of data. Okay, we have a lot of data, and the models are based on huge amount of data. Then in this case, you can use machine learning as well. And down here, this is the case where machine learning is not useful. Okay, suppose you wanna calculate payroll. Okay, it's a simple programming job. You don't need machine learning. You simply write a small program to calculate payroll. Okay. This slide shows the difference between the traditional programming approach and the machine learning approach to solve a problem. So the problem here is to recognize the image of a digit from 0 to 9. So we have 0, 1, 2, etc., right? So the goal here is to read a certain image and recognize its digit, right? So if you use a traditional programming approach, actually you have to write this program yourself, okay? I'm not saying it is impossible. It is possible, but it is definitely very difficult. You need to extract many features out of this image and do some mathematics there. So it's very difficult to do that. But on the other hand, if you use machine learning approach, things are quite simple and easy. So instead of writing a program yourself, what you do is you actually for each input image, you give its corresponding output. So for example, for this input image, you assign its output correct answer. And so this is input, this is output. And you feed this input-output pair to the machine learning program, okay? So you keep feeding this input-output pairs to this machine learning program, okay? And this is called the training. Then somehow this machine learning program learns how to solve this problem, okay? So after the training is done, and machine learning program actually generate something called the machine learning model. This can be anything depending on machine learning language program, machine learning algorithm. It can be decision tree or neural net or whatever, okay? So after training is done, then machine learning, this algorithm learns how to solve the problem and generate machine learning model. Then after that, by using this machine learning model, you can now recognize this input image correctly. Okay, that is machine learning approach. So as you can see, you don't have to write any program. Okay, you simply give input-output pairs like this, and then machine learning algorithm actually takes care of the rest. Okay, so it's very easy, simple. So this is the beauty of machine learning approach compared to a traditional programming approach. So machine learning can work on many different data types. So here in this slide, machine learning can use picture data or business data like loan application or ad information, or it works on audio data, uh, natural language data, or sensor data like this. So for each data type here, these are the typical application of data type. So for example, if machine learning is used in picture data, you can develop auto tagging machine learning application, or if it works on English sentences, you can develop language translation, machine learning application, etc. So again, machine learning, you can use machine learning in every many different data types as well. And machine learning has some similarities and also some dissimilarities with statistics. And both statistics and machine learning analyze data and need a lot of data. These are similarities between machine learning and statistics, but the similarity ends there. And so then what is the difference between these two? Let's begin with statistics. In statistics, when you analyze data using statistics, the first step you do is you have to build a hypothesis or assumption, knowledge, whatever you call it. So you build hypothesis or assumption, and then using the data you verified. Okay, you verify those hypotheses using a lot of data. That's the procedure of statistics. But in machine learning, we don't build any hypothesis or assumptions. So you simply process a lot of data and retrieve or generate knowledge out of data. Okay, there's no restriction, no need of hypothesis. Simply read data and create knowledge. Okay, that's the procedure in machine learning. So in statistics, you verify your hypothesis one at a time. You build hypothesis and verify it using data. So you do this one at a time. So the number of knowledge you can get, you can verify, is very limited. Okay, one by one. But in machine learning, there is no restrictions. You simply read data, process data, and generate a lot of knowledge simultaneously. So in machine learning, you can generate many knowledges from data. So this slide continues from previous slide. So as I said in previous slide, in statistics, you build the hypothesis first. Okay, then verify it, analyze it. Okay, so because of this, the statistics is sometimes called model-oriented method. Okay. In machine learning, on the other hand, virtually there is no hypothesis. Okay, you need no hypothesis. You simply read data, process data, and generate knowledge. So because of that, the machine learning is sometimes called a data-driven approach. Okay, statistics is called model-oriented, and in machine learning, it's called data-driven. So machine learning has a lot of advantage over statistics. Okay, so machine learning can generate many knowledges, while statistics can generate or verify one knowledge at a time. Okay, that's the advantage of machine learning. But that doesn't mean, I'm not saying you just threw away statistics out of window. Okay, but still, statistics is very useful tool in machine learning. Okay, so actually many machine learning tools are based on statistics. Okay, so in that sense, these two research areas, statistics and machine learning, is kind of helping each other. Okay, so the cultures could learn from each other. That's what I can say. So in previous slide, I said there are tons of data these days. So actually, wherever you go or whatever you do, actually we are creating data. So we can say we are datafied. So we create a lot of data. For example, if you use smartphones, smartphones are tracking our locations, and we leave a data trail in our web browsing. So whenever you click your mouse, you create log data. And also whenever you make interaction with social media, it generates data. So we generate tons of data. Finally, as we have more data, sometimes the privacy is an important issue in data science or machine learning. Uh, there are three different categories of machine learning methods, including supervised learning and unsupervised learning and reinforcement learning. So in this class, we're going to cover these two methods. So supervised learning is sometimes called the classification learning. And in supervised learning, each data actually comes with a class value or target value. And the goal of supervised learning is to predict the class value of input data. That's the goal of supervised learning. Yeah, basically supervised learning is about predicting something. Second method is unsupervised learning. It's sometimes called clustering. And in unsupervised learning, actually data has no class values. And the goal of unsupervised learning is to find the structure that exists in the data. So usually we find the group of similar data in the data in the input data. That's unsupervised learning. The third category is reinforcement learning. We don't cover it here. And reinforcement learning is a little different from supervised learning or unsupervised learning. So in reinforcement learning, suppose we have a goal, and the purpose of reinforcement learning is to find optimal sequence of actions, to achieve the goal. That's the goal of reinforcement learning. For example, if you play Baduk or Go, the goal of reinforcement learning is to find optimal sequence of actions to achieve the goal. In this case, the goal is to win the game, right? And these days, this reinforcement learning is combined with supervised learning, especially deep learning. So reinforcement learning is combined with deep learning, and it's called deep reinforcement learning. And this is kind of a new direction of the research in machine learning. There are some other machine learning methods like semi-supervised learning. In semi-supervised learning, some data has class values, and some others do not have class values. This is combination of supervised learning plus unsupervised learning. Okay, that's why we call it semi-supervised learning. So in semi-supervised learning, some data comes with class value, and some other data doesn't come with class values. So the goal of semi-supervised learning is how to improve the performance of supervised learning by using unlabeled data. Okay, that's the goal of a semi-supervised learning. Finally, we have another learning method called generative learning or generative model. And the goal of generative model is, so in supervised learning, the goal is to predict something, okay? But the goal of generative learning is actually to generate something. For example, in generative learning, it generates image or movie, or it can generate sound, or it can generate text. Okay. So that's what a generative model is about. The typical example of generative learning algorithm is like a GAN or a variational autoencoder. So these are some typical categories of machine learning methods, and we're going to cover these two methods in this class. So this picture shows the concept of three different machine learning methods. The first one here is supervised learning. Okay, so in supervised learning, as you can see, every data has class value label. So every data here has class value, let's say it's a red dot. And all these data here has class value cross. And the class value of this data is star, okay? So every data has its own class value, whether it is a red dot or cross or star. So you can use supervised learning or classification learning when every data has class value or label. Okay. So the goal of supervised learning or classification is actually in supervised. The goal is to find a line this. This is called a classifier, or you can say this is classification algorithm. So the goal of learning in this supervised learning is to find best line here. Okay, but most likely, depending on machine learning algorithm, this is not necessarily line. It's actually it's going to be very complex curve, something like that. Okay, not necessarily line. Okay, unless it is linear classifier, most likely your algorithm, your machine learning algorithm classifier it's going to be like a very complex curve. Okay, so anyway. The goal of learning in supervised learning, classification learning, is to find this boundary, whether it's going to be line or whatever, curve or whatever. Okay. So move on here is this picture shows unsupervised learning. So in unsupervised learning, every data has no label, just input data itself. Okay, no class value, no label. So so in this picture, this data forms group, and this data forms another group, and this data forms groups. So each group here means these data are similar to each other. Okay, again, these data are similar to each other, and again, we have a similar data set here. So the goal of unsupervised learning or clustering is to find groups like this. In this particular case, we find three groups of data. Okay, so in each group, the data in one particular group is supposed to be similar. Okay, so again, the goal of clustering, unsupervised learning, is to find group like this in the original data. Okay. Down here, this picture shows the semi-supervised learning. So in semi-supervised learning, actually, it's combination of supervised plus unsupervised learning. So that means some data has labels in it, but some other data doesn't have any label, it's unlabeled. Okay, it's a combination of both. So as you can see here, this black square means unlabeled data. It has no class value there. But there's some labeled data too. This red data is labeled data. This cross is labeled data, and this star is again labeled data. So this is mixture of labeled data, unlabeled data. So what you're gonna do here in semi-supervised learning is we're gonna improve the performance of supervised learning, the performance of classification learning by utilizing unlabeled data. Okay, if you come here, supervised learning, again, the goal of supervised learning was what? To find a nice, best boundary like this. Okay, again, it doesn't necessarily mean this boundary is line. Okay, most likely it's going to be a little complicated boundary curve, whatever. Okay, so anyway, the goal is to find the boundary between these different class values. So the goal of semi-supervised learning is the goal is the same. You want to find a nice optimal boundary like this. But in this case, semi-supervised learning case, you're going to make use of unlabeled data. Okay, so in semi-supervised learning, by using this unlabeled data, we're gonna improve the performance of supervised learning. Okay, so that's the basic idea of a semi-supervised learning. So we don't cover semi-supervised learning, but that doesn't mean this area is not important. This is important, but yeah, we don't cover it because you have so many algorithms to cover. Okay. This slide is a little replicate of the previous slide. I'm going to explain this supervised, unsupervised, semi-supervised learning by using more examples here. This is an example of label data. Okay, so we have, let's say, we are dealing with the image data. So this is input data, and for each data, input data, you give a label or class value. So in this case, this is a picture of cat. Okay, so this is input data. This is a class value or label. Okay, so every data has its own label or class value. So you have another input data, and we say this class value is dog, label is dog. Okay. So again, in label data, that means every data has its own label or class value. Okay. This is label data. And unlabeled data, on the other hand, is we have input data, but there is no answer, no label, no class value. Because we have input data, like image, whatever, but that's it. Okay, there is no label, no class value, no answer, okay, whatsoever. So you have another input data, but there is no, again, no answer, no label. So this is example of unlabeled data, and this is example of labeled data. So in supervised learning, we are dealing with label data only. Okay, as you can see here, every data comes with class value or label, right? So a supervised learning, take care of label data only, something like this. In unsupervised learning, it it deals with unlabeled data only, something like this. Okay, so if data is your data has no class value, the only option you have is unsupervised learning. Okay, so unsupervised learning, it deals with input data only, no unlabeled data. Okay, so here this data has no class value here. And finally, semi-supervised learning, then is combination of both. Okay, some data has label, some data is labeled data, and some others are unlabeled data. So semi-supervised learning. So how to improve the supervised learning performance by using unlabeled data. That is the goal of semi-supervised learning. Okay, now let's begin with supervised learning, also known as classification learning. You can consider a supervised learning algorithm as a function which look like this. So here, the F is the classification algorithm. So what it does is it read a certain input X, and then it generate a certain output Y. Okay, so in that sense, you can consider classification algorithm F as a function. Okay. So what happened here is I said in supervised learning, every data comes with a class value or a target value, right? Which is output. So in supervised learning, every input comes with output Y. Input X1 comes with output Y1. Y here is target value or class value. So every data, every input comes with output, okay? So you feed these input-output pairs to this classification function or algorithm. Okay, you keep feeding them. Then this classification algorithm somehow figure out or learn how to map from input data X to output Y. Okay, it learns automatically how to map from input X to output Y. Okay, and this process is called training. So when the training is done, now you give a new data X to function F, okay? Then this classification algorithm F now generate its correct output, okay, Y. So that's what happens in supervised learning or classification, okay? Again, I'm going to emphasize that this supervised learning algorithm is an implementation of a function. This slide shows some example of classification function. So I said in previous slide, classifier, the classification algorithm is kind of function. So it's in say we have classifier F, okay, and if you give this image, okay, then this classifier classification algorithm function returns output, returns apple as an output. Okay, so it's like saying this image is apple. Okay, and let's say you give this image as an input, and this classifier gives output saying it's cow. If you give this input, okay, like go image, then this classifier say next move is A7 whatever. Okay, it tells you the next move. This is example of AlphaGo. And let's say you give this image, then this classifier recognize it, and this it says, well, this is digit 3. Okay. So again, you can assume the classification algorithm classifier is kind of a function. Okay. So classification learning actually consists of two phases, two steps: training and testing. So in training, yeah, I told you the supervised learning, classification learning, every data comes with output or target value, right? So in this case, suppose we are dealing with image data, then each image comes with label or a target value. So in this particular case, let's say for this input image, each label is apple or something like that, okay? So each input comes with label, and you give this pair of input output to the classification function, okay, machine learning model or classification function, whatever you call. You keep feeding them, then this function or machine learning model learns, okay, learns how to map from input data to output label, okay. It automatically learns how to map from input to output, and this process is called training. So in that sense, this classification function is a mapping function between input and output, okay. So when training is done, then when you have new input data like this, then you give this input to this function or machine learning model, which was trained here, okay. Then this function generates its prediction, and this prediction is supposed to be a correct output of this input data, okay. That's the process of testing. So actually, every classifier or classification function belongs to either a linear classifier or nonlinear classifier. And this slide is about linear classifier, and the next slide is about nonlinear classifier. So I said the classifier is a function, and if you visualize the classification function, you can say the classifier is actually the boundary which separate different class values. Okay, that's a kind of visualization of classifier. So in this case, let's say we have two class values, blue and red. Okay, so the goal of classifier is to find a boundary which separates these two class values. Okay, so again, a classifier is function, and or in other words, classifier is the boundary which separate different class values. So when I say linear classifier, then if the boundary is straight line like this, then we say this classifier is linear classifier. Okay. Or if this boundary is not linear, like something very winding or curved, like in next slide, and that classifier is called non-linear classifier. Okay. So the definition of linear classifier is the boundary, okay, which separate different class value is straight line, okay, then the classifier is called linear classifier. So as you can see here, this linear classifier can be represented like this. As you can see, this is linear line, okay, that's why this is called linear classifier. So every classifier belongs to either linear classifier or non-linear classifier, okay. But the problem of a linear classifier is this classifier is very easy, very simple, okay. But problem is in almost every real-world application, these class values are not linearly separable. Okay, the distribution of class values is much more complex than this. Okay, so it's almost impossible, okay, to use linear classifier to separate different class values in real-world application. Okay, so in that sense, the linear classification is very limited in real-world application. Okay. So the previous slide was about the linear classifier, and this slide is about a non-linear classifier. So as I said, if you visualize the classifier, then you can say the classifier is the boundary which separate different class values. So in this particular case, we have a blue class and red class. And if you use linear classifier, no way you can divide this blue class from red class. That's impossible, right? So you definitely need a non-linear classifier, a winding curve like this to separate blue class from red class, right? So that's why we need non-linear classifier. So actually, in almost every real-world application, these class distributions are very, very complex, right? So because of that, it's almost impossible to solve a real-world problem by using linear classifier, okay? Real-world problem is much, much more complex than linear problem. That's why almost many classification algorithm is non-linear algorithm, okay? But one advantage of linear classifier is if you are able to solve a problem using a linear classifier, then it is very, very easy to find optimal answer, okay, by using linear classifier, okay. But on the other hand, if you use non-linear classifier, it is very, very difficult to find optimal classifier in non-linear classification. So actually, there are many different classification algorithms to choose from. We have decision trees, we have SVM, we have neural net, and random forest, ADA boost, and K nearest neighbor and deep learning, and we have naive Bayes or GAN, and many more. Okay. So we cannot cover all algorithms in this class. So we're gonna cover from decision tree to deep learning here. Okay, we don't cover these things. So we're gonna cover these algorithms in this class. Another thing is we have so many classification algorithms. So which one is the best one? So these days, people say deep learning is the best classification algorithm. Okay, so we're going to talk about this issue in more detail when we talk about no free lunch theorem. Okay. So we have seen the short introduction of a classification method. Let's move on to another topic, which is clustering algorithms, also known as unsupervised learning. So in this class, we're gonna cover three of them: the k-means and agglomerative clustering and the EM. So we're gonna cover these three later in this class as a separate chapters. The goal of clustering is to find the structure of data space. So, but most likely you're gonna find the groups of data space which look like this in this. So, for example, here we have two groups, and in each group, data in this particular group are supposed to be similar. And again, in this group, all data in this group are supposed to be similar. So again, the goal of clustering is to find these groups. As the machine learning technology advances, these days we see some remarkable results from machine learning method, especially in the area of image processing and speech recognition. We see some very nice results, which is shown here. So this shows the performance of machine learning, especially deep learning, in the area of voice recognition, speech recognition. So here, this dotted line represents the performance of human voice recognition, and this red curve represents the performance of deep machine learning, especially deep learning. So as you can see here, it keeps growing, and around 2017, this deep learning performance now outperforms the performance of human. And also here, down here, this shows the performance of image recognition here. So again, this dotted line here is I'm sorry, this line here is the human level accuracy. So this blue bar shows the performance of, again, deep learning. So again, and around 2017, this performance actually exceed the performance of human level. So yeah, roughly speaking, in the area of image recognition and speech recognition, the deep learning, machine learning, especially the deep learning method, kind of outperforms the accuracy of human level. Yes, this is another interesting application of deep learning. So here is you train your deep learning, in this case again, and using a lot of the Van Gogh painting. Okay, so your GAN algorithm is trained by using lots of Van Gogh painting. Okay, and then later when the training is done, you give a new input image like this. Okay, and then you ask the algorithm to paint this. Okay, then the algorithm draws something on top of this. Okay, and so this is the result. Okay, this is based on the original image, but it looks quite like a Van Gogh, right? So that's the very interesting example of the deep learning, especially again. And down here, what's happening here is, for this case, you have lots of night images. Okay, you have a lot of images at night. Okay, you train them using night images. Okay, and then you give this day image as an input. Okay, then ask the algorithm to transform this into night image. Then this is the result. So this original input day image now is converted to night image. Something similar happens here. So you have a lot of grass image here, okay? Field image here. Actually, this is summer time. And then when you give this winter image here, then the algorithm is going to change this winter image to summer images. Okay, so that's another very interesting application of deep learning. AlphaGo is the one of the most famous application of machine learning, and this AlphaGo plays the game of Go or Baduk. And as we all know, this AlphaGo has beaten the top players in the world. This AlphaGo uses supervised learning and reinforcement learning. In short, is called a deep reinforcement learning. So it consists of two deep neural networks. The first one is policy network. The second one is value network. These are deep neural networks. So that's AlphaGo. More recently, there is another interesting program called AlphaCode. What AlphaCode does is you give us a certain problem description like this. Then this AlphaCode actually read this problem description and generate program code like this. So that's AlphaCode, and this is not perfect, okay, not yet. But actually, this program ranked within the top 54% in the programming competitions. So it's quite impressive result. Okay, so this is another interesting, more recent application of deep learning and machine learning. There is an interesting theorem called no free lunch theorem in machine learning. The algorithm goes like this. Suppose there are two classifiers H1 and H2. Classifier is a classification algorithm in machine learning. So let's say you have two arbitrary classifier H1 and H2, and also suppose H1 shows better performance than H2 in some domain D1. Okay, domain is data. Okay, so H1 is better than H2 in some data D1. Okay, then there are some other data D2 where actually H2 is better than H1. Okay, so it goes like this. Okay, so for a classify H1 and H2. Okay, H1 is better than H2 in some data D1. Okay, but for other data D2, okay, then in D2, actually H2 is better than H1. Okay, and there always exists such data D2. Okay, that is a no free lunch theorem. Another way of saying this theorem is, so if you compare two classifier H1, H2 for every possible domain, okay, so suppose, okay, this is unrealistic, but suppose you have every possible domain you can imagine, okay, suppose you have that data, then if you compare this classifier H1, H2, actually there is no winner. These two classifiers are actually equivalent, okay? So in this case means suppose you have every possible domain you can imagine, okay, in your world, then no classifier is inherently better than the other, okay? That's no free lunch theorem. So if you have every possible data, two classifiers are same. Then the next question is then why do we prefer one method, one algorithm to others? Okay, for example, people prefer deep learning these days to other methods. Let's say decision tree. Okay, and also we know deep learning or deep reinforcement learning shows better performance than other algorithms, right? So why is it? The reason is we cannot have every possible domain. So here it says if we have every possible data, then these two classifiers are equivalent. But this is unrealistic. Okay, you cannot have this. We cannot have every possible data domain. The reason is our world is full of biases. So when I say bias, I mean every physical law or chemical law or mechanical rule or our social law, science, or whatever, everything, okay? And these are, when I say biased, these are the example of biases here, okay? Yeah, for example, people cannot live under the sea, we cannot fly, okay, etc. Okay, everything is bias, okay? Our world, we are surrounded by biases, okay? So because of these biases, the data we use, okay, this data, domain data, is generated from our world, and because of these biases, this data also has biases in it. So every data we have has bias in it, okay? So machine learning is using this data, okay, and the goal of machine learning is actually to learn these biases in the data correctly and efficiently. So we're gonna learn many machine learning algorithms, and actually the goal of machine learning is to learn the bias in the data correctly and efficiently. Okay, so learning is about learning bias. Okay, so learning bias is the most important key in human learning and machine learning as well. So in human learning, as a human learning is about learning bias in nature, and machine learning is actually about learning bias in data. Okay, so that's the kind of summary of no free lunch theorem.